Hey everybody, it's Miss Sullivan, and today I'm talking to you about scientific notation, just like it says at the top, scientific notation. Scientific notation is essentially, it's going to look like that. That's what the number looks like when you write it down. And at the moment that might not mean much, but we'll find out what it means in a minute. What's important to remember, and we're going to start on this side, is that scientific notation involves index notation. Most particularly this time, it's a power of 10. You're going to multiply something, in this case a significant figure, but don't worry about that for a second, to a power of 10. So before we start, it's really important that we remember place values. So this might seem silly, but just as a reminder, we've got millions, hundreds, thousands, tens of thousands, hundreds, tens, units. There's your decimal. So all of those are whole numbers, and our fractions, our parts of wholes, are tenths, hundredths, thousandths, 10,000ths, and obviously it keeps going this way and up that way. So let's write a quick little number in just so that we remember how this works. If I had, I don't know, 2, 7, 5, 6, that would be 2,756. If I had 0.1, we've got 1/10, or perhaps I've got something like 7,456,812.2795, knowing that that's 2/10, 7/100, 9,000ths, and 5/10,000ths. So as you can see, we're starting to work with really big numbers. But we'll be coming back to that in a second too. So just a little reminder about place values before we start. So coming back to this idea of index notation, what we were just looking at there is our decimal system, which is built on base 10. Interestingly, it's built on base 10 because we have 10 fingers. So it's also really important to note when we're working in base 10 that the index is, so the little number up here, this little 3 up here, how many times are going to multiply 10 by itself? So this would be 10 times 10 times 10. The number of zeros is the same as the index number. And for negative indexes, the 0 in the units column is the first 0. Okay, what does that mean? I'd like you to copy this down because this is going to be helpful. So let's have a look. It's very similar to what we did when we were learning about index form. So I'm going to start here with 10 to the power of 0. Now, because we just did index notation, we know that anything to the power of 0, except for 0, of course, comes to 1. So let's move up, and we'll have 10 to the power of 1, 10 to the power of 2, 10 squared, 10 to the power of 3, 10 cubed, 10 to the power of 4. So we'll work up from here. Anything to the power of 1, that just means one lot of itself. So 10 squared is 10 times 10, so we get 100. 10 times 10 times 10, 1,000. 10 times 10 times 10 times 10, 10,000. So we can see that when we're moving in this direction, we're multiplying everything by 10, which means when we move in this direction, we're going to be dividing it by 10. So if we keep dividing by 10, when we get down to here, remember our negative indexes. 10 to the power of negative 1, 10 to the power of negative 2, 10 to the power of negative 3, 10 to the power of negative 4. Now, I could write that as 1/10 like that, or I can write 1/10 as a decimal, 0.1. This could be 1/100th or 0.01. So let's count those zeros. -1 is a 0. So when I said here, note, index equals number of zeros, So let's check. 4 to the power of 4, I've got 1, 2, 3, 4 zeros. And here I've got, for negative index, 0 in the units column is the first 0. So let's check here. How many zeros? 1. It's the one in the units column. Here I've got 2. 1, 2. We start in the units column, not behind the decimal, in front of the decimal. This one's obviously going to be 1 over 1, 2, 3 zeros, which is going to be 1,000th. 0, 0, 1. Again, 3. 1, 2, 3. Cool. And finally, 1 over 10,000, which is 1.0001. I'm dividing each time by 10. And then obviously moving in this direction, it would be multiplying by 10. So just a little reminder. Index number, number of zeros. Negative index, number of zeros, but you've got to start with the 0 in the units column. Excellent. So half of index notation, half of scientific notation is all about index notation. It allows us, you can see that by the time we got to 10 to the power of 4, we were already at 10,000. So 10 to the power of 19, we're looking at giant numbers. So the second half of scientific notation, we've got this, we're all sorted here, is this concept of significant figures. So you multiply a significant figure by 10 to the power of however many zeros you need. So I think the best way to talk about this is something like the population of Australia. So we say the population of Australia is 24 million. So 24 million people. We know it's not actually 24 million people. It'd be 24 million, 977,462. Oh, now it's 63. Oh, it just dropped it back down to 60. People are being born, people are dying, people are moving here, people are leaving here. 24 million is an estimate. And really, as a regular person, that's all I need. It's also really hard and incredibly expensive at any point in time to work out exactly how many people live in a country. So I just Googled and it said that in 2018, so obviously drawn from the census data, because we did a census last year, or maybe it was the year before. Anyway, we've done a census recently and the figure for 2018, based on the modelling, is 24,772,247. All right, 24,772,247. If I look at this 772,000 bit here, and I remember my rounding rules, that's a long way. This very next number here, that's a long way above 500,000. When we hit 5, we can choose to go up or and if we're below 5, when we hit 5, we can choose to go up or down. But if we're below 5, we go down. If we're above 5, we go up. So really it would seem right to say that the population of Australia is actually 25 million people. That's a lot closer to 24,772,247. So it doesn't really, for the moment, we'll just sort of push the specifics aside and we'll look at this idea of significant figures. So we've got to look at what is the first non-zero digit. To work out what is the significant figure, we look at what's the first non-zero digit. Well, here it's a 2. So it's 2 and 4 followed by zeros. So I can guess that this number has been rounded. That's not the actual figure. It's an estimated figure. So what's really important to note here is that not all zeros are insignificant. You've got to focus on the context. So if I said that there were 30 people in a class, that might not be an estimate. There might actually be 30 students in a class. And that's important when we get down here. So if we look at the example, 24 million, we say that that has two significant figures, 24. When I said there were 30 kids in the class, 30, I'll just write it in here, also has two significant figures. Because I know the context, I actually know that that's not, this 0 here, that's not an estimate. It's the actual number. So let's have a look at, that was obviously the 2017 population. So looking at the 2017 actual figure, let's look at it and we'll provide 3 significant figures. So then we start here and we look at the 2, the 4, and I'm going to round this up to 800,000. So 24,800,000, if I have 3 significant figures, it is a much more accurate estimate. 24 million versus 24,800,000, 3 significant figures gives me a more accurate idea of how many people are actually in Australia. But what's important for us to remember here is this idea of significant figures. So the fewer the number of significant figures with giant numbers and really, really small numbers, the lower the level of accuracy. So when we're looking at this scientific notation concept, we join a significant figure and we multiply it by a power of 10. This is really important for scientists because they work with giant numbers and minuscule numbers. And if you were just writing and rewriting them all the time, it'd be almost impossible. Some of the numbers are just enormous. Think about measuring the universe. Numbers like this, how many zeros have we got here? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are massive sorts, and that's a small number for people who are working in, any sort of examination of space. So when we have a look here, rather than writing this full number, scientists using scientific notation take the significant figure, which here is 2, and they multiply it by 10 to the power of 12. So the significant figure multiplied by 10 to a base. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's just a much more efficient way of writing that. We need to have a look here with tiny numbers. So you'll notice that this also has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros with a 2. Again, 2, what's the first non-zero digit? Start at the left, move along. Oh, it's 2. 2 is my first non-zero digit. And now I'm going to multiply it by 10 as my base to the power of negative 12. Because as we saw before, when we've got our negative numbers, we're working on the other side of the decimal. So I've got here copied the examples which I'm about to show you, but before I move on, really important to notice that this significant figure must be a number between 1 and 10. It must be a number between 1 and 10. If not, I've got to basically divide it by 10, and it might even be 10 to a power. I've got to turn it essentially into a decimal. This is why it's really important that you copy down these examples. So let's have a look here. 27 million. Let's write this in scientific notation. I need to look for the significant figure here. I'm going to think to myself, I don't know the context of 27 million. I don't know if that's an accurate measurement of something or if it's an estimate. I'm thinking it's probably going to be an estimate. So if I don't know, I'll assume it is. So in this case, I look for the first number that's not a 0, it's a 2, and a 7, followed by 1, 2, 3, 4, 5, 6 zeros. Now, I could write 27 times 10 to the power of 6. But this is not a number between 1 and 10. I've got to turn that into a decimal so that it's a number smaller than 10. So to turn that, I basically have a look at how many, I've really got a decimal here, count how many times I have to move the decimal to make this 2.7. 1, 2, 3, 4, 5, 6, 7. So the correct index notation is 2.7 times 10 to the power of 7. Let's practice on this one. Here I've got more numbers. So there's my first number that's not a 0, but I've got 1, 2, 3, 4, 5, 6, 7 significant figures before my 1, 2, 3. Now this That's definitely 10 to the power of 3. Cool, but that's definitely not a number between 1 and 10. To make it a number between 1 and 10, I'm going to need to remember that this really finishes with a decimal and move it. 1, 2, 3, 4, 5, 6, 7, 8, 9 places up to here. So this becomes 7.530103 times 10 to the power of, what was it again? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the power of 9. Here's a good opportunity for me to point out that sometimes zeros are significant figures. There's a reason that this was the only bit that was rounded. I don't know what that reason is because I don't know the context of this number. I don't know what this number actually applies to. Maybe it's a measurement of something. I don't know what this number potentially measures. So there's a reason that they rounded it from there. So this 0 here and that 0 here, zeros can be significant figures. Excellent. Let's move on to this one, and we're working the other way. So what's my first number that's not a 0? Oh, there it is. 8854. I've been given 4 significant figures. So again, I've got to make sure 8854, 8,800, that's not a number between 1 and 10. So I'm going to move my decimal place. This time my decimal's over here. 1, 2, 3, 4, 5. I moved it 5 places and now I've got 8.854. That's a number between 1 and 10. So scientific notation here, this number looks like 8.854 times 10. How many times did I move it again? 1, 2, there was 1, 2, 3, 4, 5. 10 to the power of negative 5. I'm moving the decimal this way. So let's have a look at this one. Again, I've got 4 significant figures, but that is certainly not a number between 1 and 10. 5.238 would be a number between 1 and 10. So again with the decimal and the moving. 1, 2, 3, 4, 5, 6, 7. Brilliant. 5.238. That's definitely a number between 1 and 10. So expressed in scientific notation, it's 5.238 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, negative 7. Excellent.